at part 2 of the review. This is lecture 2. So if you didn't watch lecture 1, go watch lecture 1. All right, so increasing, decreasing function. It says a function f is increasing on an open interval I if for any choice of x1 and xn. What the heck? The problem that a lot of students have in a math class is they want to pick it up and read it like a novel. You can't read math books that way, okay? Even my notes. What you want to do is, when you're given a definition, is to kind of go through, and say, okay, well, I know what an interval is. I have some interval here. I understand this x1 and x2 because those are just values here, where x1 would be to the left since it's less than. All this is saying is then if I go up to the function, okay, f of x1 and then f of x2, that this one would be lower. So that is the definition of an increasing function. Same for decreasing, except now I would see f of x1 is greater than x2. And then for constants, they stay the same. So the point is that whenever you have something that you don't understand the definition, ask me and I will try to explain it, in a way that normal people, not us nerds, can understand. All right, so why do we care about increasing, decreasing constant functions? Well, we definitely like to know about minimum and maximum functions. We like to know where we hit the max, say, of a drug, or where it even bottomed out, and you're going to see everything is not parabolas. So in the past, you may have learned like a vertex formula to find these values. We're going to find a way using calculus to be able to find these values. Transformations, maybe you kind of sort of remember, a lot of students remember x squared parabola, negative x squared, flips it upside down. This is a good just little sheet to remind you of how we can move functions around. All right, composite functions, big important part of this course. I will review again later, but all a composite function is a function within a function. And so I have an example here. It says oil is spilling from a well at a rate of 2,500 gallons per day. At this rate, the radius of the circular pool of oil will change at a constant rate of 4 miles per day. Write an expression that represents the radius of the oil slick at time t, r days after the leak has started. Well, it just says here that we're talking about a constant rate. Constant rate would be linear. But now when I'm looking at a radius, okay, I'm looking at the area. Okay, so it says at this rate, the radius of the circular pool, this is what's changing. But now I want to know how much has leaked based off of the area formula. And in this case, we're going to say in a circle. And so we use this formula, pi r squared. And where the r is actually a function of time that was given to us in the miles per day. So I plug everything in that I know. Okay, it says recognize this relationship, and the change in area is dependent upon the radius as a function of time. And so I simply plug that in, and now I have something that I can use to find the area in 4 days. I plug in 4 for t, okay, and get my answer. So you're going to see a lot of things like this is going to be based on, first of all, understanding that you have a function within a function, right? And then to be able to, and don't forget your units. What would your units be? Leave it up to you to figure out that area there. But you're going to see that we're going to analyze when you do one thing and you get something out, then you can put it back into another function. Average rate of change. This is where the course is really going to start and get good. Remember I said in the last lecture that we tend to like the slope as, instead of saying the change in y over the change in x, we like this delta y over delta x, and it's said that same way as functions. This difference quotient, most of you probably learned at the end of your pre-cal class, this average rate of change is the slope. So what we're going to look at though is, if I want to know how fast something's changing, the rate of change on average of a curve, I could do it by picking 2 points anywhere on that curve and connect the dots with a line. When you have 2 points connected on a curve, that's called a secant line. Now, why do we care? Because I could say from this point C to that point X, on average, how is it changing by using the slope formula? And that's all this is. It's a whole bunch of different ways, the slope of a secant line, to write it depending on your 2 actual data points. So it says, suppose that you are at a red light and then the light turns green. You put your foot on the accelerator because you're not sitting there on your phone, right? And the car increases its speed from 0 to 50 miles per hour in 5 seconds. What is your average rate of change of speed? So on average, we're looking at the change in speed over the change in time. You started at 0, okay, so your change in speed, and got up to 50. Start time is always 0. I don't know why students want to say 1, but start time right now is 0, and from 0 to 5 seconds. So I can plug in those values and I get 10, and then I could see my change in speed, miles per hour, and then my change in time. And I could even, manipulate this to the same units, but this gives me good enough information that I can see my average rate of change. All right, hopefully you kind of sort of remember some of the rules of exponents. We will use these a lot. If you multiply, what do you do with the exponents? If it's outside the parentheses, if you divide outside the parentheses here, this is a good little cheat sheet to remind you when you multiply, you add the exponents. This is brought inside and being multiplied. When you divide, you subtract the exponents. And this is the same thing being brought inside, just showing with a fraction, to multiply the outside by the inside. And then we talk about different exponential functions, graphs that rise very quickly, definitely things like diseases. Okay, let one person get sick and watch what happens. All of us get sick. We like the decay function. I will say that I typically prefer, by my little pencil here, I don't tend to prefer this format. And this kind of will bring back and see if you remember something. So if I have 1/2 to the x, we just said by the exponential formula or property that I could put the x on both pieces here. Well, anything 1 to any power is just 1. Do you remember, this is something very, very important, that you can bring this up to the top. What happens to the exponent? Do not forget that. That seems to be something that a lot of students don't remember, okay, that you get a negative exponent. Do not forget that. In fact, if you go back here, okay, looking at, here's the 1 piece that I actually did, and then notice the negative exponents. This is a good cheat sheet to make sure you understand each one of these rules. All right? I tend to like to write this better like this because this says, oh, positive exponent going up, negative exponent coming down. Just helps me remember so I don't have to deal with that. Then when you got into logarithms, I realize a lot of students struggle with logarithms, but they're just exponents. They have the same exact properties. Some of the main properties when you're multiplying, guess what you do with the exponentials? We talked about multiplying, you add the exponents, look what happens with the logs. Exponentials, you divide, you subtract, look what happens with logs. So some nice properties that we will review and use in this course. Next, you got to your pre-cal part where you talked about circles, okay, and we talked about the radius, we talked about the center of a circle. We could actually get an equation of a circle. You probably remember this quite well because this is what you used a lot in your pre-cal class where you started at the origin, okay, the 0, 0. Same thing, right, because your h and k is the center, so if I plug zeros in there. And then that brought you to learning about angles and trigonometry and your favorite, the unit circle. I don't ask you to memorize the unit circle. In fact, it's kind of easy because all you have to do is learn one quadrant and then you can do everything from there, but I don't ask you to memorize it. I will talk about some of these identities. Ooh, remember those? But I typically show them a lot when we do some proofs, okay? And so they're more of, did you kind of sort of remember this? No, well then guess what? We'll Google it or we'll go look it up somewhere. Probably more importantly are these graphs, because this is something that's showing things in nature that are repeating, like you taking a pill and then it starts to leave your blood system and then you take it again and so on. All right, once again, I know that was fast and furious. This is review material. So hopefully the majority of that you're like, nah, kind of sort of remember. Some you might have to, go back and review again. As I do problems in this class, if they involve review material, I'll review them again. All right, that's the end of the first lecture.